Did you know that the first active communication satellite, Telstar, could only relay television signals and telephone calls for about 20 minutes per pass? Fast forward to today, and we have satellites that can provide uninterrupted services 24/7. From the era of Telstar to the present day, the evolution of satellite communication has been nothing short of a technological marvel. The key to this revolution? Radio frequency signals, the invisible threads that connect our world through the sky. These signals are the lifeblood of satellite communication, facilitating a constant exchange of information between satellites and ground stations. Satellites are equipped with specialized transponders that operate in specific frequency bands, such as the C-band, Q-band, and K-band, receiving and transmitting data to and from Earth. These bands are like highways in the sky, each carrying a unique set of data, commands, and updates between ground stations and satellites. Indeed, the strides we've made in the field of satellite communication are nothing short of remarkable. Imagine you're in a crowded party, trying to have a conversation with a friend across the room. The noise from the crowd is like the uplink frequency, and your friend's reply is the downlink frequency. In this bustling party, you're the ground station. When you shout out a message to your friend, that's akin to the uplink frequency. This is how ground stations send signals, which could be satellite control commands, software updates, or specific data requests, up to the satellites. Now your friend, acting as the satellite, receives your message. Equipped with onboard computers, satellites decode these signals, process the information, and execute specific actions. This is where the downlink frequency comes into play. After processing your message, your friend responds. This response, transmitted back across the noisy room, is like the data that satellites send back to Earth. This data can be anything from images and sensor readings to scientific data or other information collected by the satellite. So, essentially, satellites and ground stations are having a constant party conversation in the language of radio frequency signals. Consider a satellite as a high-tech postman, but instead of letters, it deals with signals and data. Just as a postman has an address to deliver mail, satellites receive specific signals from the ground station. These signals are like commands, instructing the satellite on what to do next. Maybe it's a software update, a command to change course, or even a request for specific data. Equipped with sophisticated onboard computers and systems, satellites don't just receive these signals, they process them. It's like the postman reading the address on a letter and understanding where to deliver it. The satellite decodes these commands, understanding what is being asked of it. But the magic doesn't stop there. The satellite then executes specific actions based on these commands. It might adjust its course, collect specific data, or update its software, all while orbiting thousands of kilometers above the Earth. With their advanced onboard systems, satellites do much more than just delivering messages. They process, interpret, and act on them. Think of the ground station as a catcher in a baseball game, ready to catch the ball, or in this case, data, thrown by the satellite. The satellite, swinging high above the Earth, sends its data down to the ground station, just as a baseball player throws the ball to the catcher. This ball, however, is not a tangible object, but a torrent of images, sensor readings, and other valuable information. The ground station's dish antenna, much like a catcher's mitt, is designed to catch these signals. Once the data is received, it's like the umpire calling safe. The data is then processed and may be sent to a network operations center or a data processing facility for further analysis, storage, and distribution. Depending on the mission and purpose of the satellite, this data can be used in myriad ways. From scientific research to weather monitoring, the data caught by our catcher ground stations has innumerable uses. As we look to the future, the sky is literally the limit for advancements in satellite communication. The realm of possibility is expanding, driven by innovations in technology and hardware. Phased array antennas, for instance, are paving the way for more flexible and efficient communication systems. Unlike traditional dish antennas, these advanced devices can electronically steer their beams, enabling rapid switching between satellites. Meanwhile, software-defined radios are transforming the way satellites communicate. By replacing hardware components with software, these radios enable dynamic adjustment of frequencies, modes, and protocols, enhancing the adaptability and resilience of satellite systems. But the real game changer could be satellite constellations. Imagine dozens, hundreds, even thousands of satellites working in harmony, blanketing the globe with coverage. This could address the challenges of latency and global reach, providing uninterrupted, high-speed connectivity even in the remotest corners of the world. From the first Telstar to the future constellations, the journey of satellite communication is a testament to human ingenuity and innovation.